All right, hello everyone. In this video, I want to talk about some things in Objective 13, specifically talking about some applications of sine and cosine. And this is actually one of my favorite lessons to talk about in the whole semester because we finally get to apply the math to real life stuff. And I think everyone likes that in general. And also my research area is in math ecology. So the kind of stuff that I think is really interesting is taking math and applying it to real life stuff in ecology. And this is like the beginning steps of some of the stuff that I do in that research area. So excited to be talking to you about this today. So there's a whole lot that we can do when we're trying to model real life things with sines and cosines. And the reason that sine and cosine are really helpful to do that is because sine and cosine have a behavior unlike anything we've ever seen before because they repeat, right? They wiggle, they go up and down, and they do that for forever. They do this oscillatory thing for forever. And none of the functions we've seen before have done that. X squared goes up forever, but that's not like repeating. It doesn't go back to where it was before. Or the square root function, it doesn't have any sort of repeating, or even exponentials and logs. Like there's no repeating in that. But there's a lot of things in everyday life that do repeat. And so for these things that do repeat all the time, it's a super good way to model these is with these exponential functions. So just to kind of sketch out, what do I mean? They repeat, they go like this, right? That's almost the sine graph. I didn't do a great job sketching that there. Or I could do a translation of a sine graph that maybe looks like this, right? And it could be up high or whatever. So they repeat a lot, and that's cool. So what are some things that repeat monthly or daily or yearly? One thing that might repeat is like the temperature. And that might happen in a couple of ways. Temperature might repeat kind of daily. If you look at a couple of days, you might have, on this is Sunday, Monday, Tuesday, we're going to have a high and then a low and then a high and then a low and then a high, right? So you'd have a daily temperature or even yearly temperature. If we're looking at January, February, March, it's cold and then it gets up and I'm going to run out of space, but it's going to go back down again and then up again, right? It's going to have that repeating behavior. And in January, it's going to be cold again. And in the next January, it's going to be cold again, year after year after year. Another thing that might repeat is like tides, right? Ocean tides, right? We have high tide and then we have low tide and then we have high tide and then we have low tide. And that happens over and over and over again. And if you live near the ocean, if you've gone to the ocean, you've always had to go check when is going to be high tide and when is going to be low tide. Well, there are functions, there are sines and cosines that are used. People model these things with sines and cosines. So that's how we answer these things. Anything with oscillatory behavior. So anything that oscillates, like a spring or so, like sometimes like a bouncy chair might bounce up and down and up and down. That's an oscillatory behavior. So there's a lot of physics applications where maybe we put a weight on a spring and it goes up and down and up and down and up and down. And that's going to be modeled with a sine and a cosine. So all sorts of things repeat like that. And so it's really great to be able to use sine and cosine to model these phenomenon. So the first example here I want to talk about is trying to come up with a model for the average monthly temperature in Nashville, Tennessee. So we could basically say this is Clarksville's data because that's probably not that different. And so what I have here is that maybe I should have made these dots bigger, but I have these data points. They correspond to all the data that's in here. So on my x-axis, I have the month, where 1 is January and 2 is February. And then on the y-axis, I have the temperature or the average temperature. And that's in Fahrenheit. And what I would like to do is create a sine or cosine or some sort of function to be able to model this. And so what I might do is I say, oh, looks like I've kind of got a sine wave here. And so I might grab my pencil because I will mess this up if I try to do it in pen. I might try to sketch this and say, well, this looks, if I really wanted this great, I'd go to a computer. But this looks about like the sine wave I have here, and it's probably going to repeat and repeat. And so my question is, well, what is the equation of the function that I just sketched here? It's probably some sort of sine or cosine, but I don't think the amplitude is 1, and I don't think the period is 2 pi. So one thing we might ask is, well, what is the period of this? And to do that, I might look at where does it start repeating and end repeating, right? Where does that start and stop? And what is that distance? And well, if we're talking about the monthly temperature over a year, it better be 12 months, right? It takes 12 months to repeat in this cycle. So my period is going to be 12. So how can I get my B from that? My period helps me get my B, but remember the period is not the B. The period is related to the B. And our formula is that our period is 2 pi divided by B. So I can use this to solve. I can say that 12 is 2 pi over B. If I multiply both sides by B, I get that 12B is 2 pi. I'll divide by 12 and say that B then is pi over 6. Cool, pi over 6. So I've gotten this letter. Okay. Another thing I might want to start thinking about is like, how stretched is this and how moved up is it, right? And to do that, I want to think of, well, what is my low temperature and what is my high temperature? That's going to tell me like, how far do I need it to go up? So let's see, my high temp, let's see, it looks like my high temp is 83 degrees. And my low temp is 40, right? And if I do 83 minus 40, that's 43. So that means that I need this whole distance here to be about 43. Right? From the high to the low needs to be about 43 because that's how much I need to go from one to the other. Well, let's see. That's not quite my amplitude. You might be tempted to say, oh, well, then 43 is my amplitude. But remember that 43 is my distance from the midline up or the midline down. So really, if this whole distance is 43, then half of that would be my amplitude, right? Then my amplitude, or at least the absolute value of my amplitude, is going to be 43 divided by 2, which I should have done this ahead of time. 43 divided by 2, 21.5. Okay, cool. So I don't quite know yet if this is going to be a negative 21.5 or 21.5. I don't know yet if I maybe want a reflection. But we can think about that there. Okay. So I have my A, I have my B. Next, we might figure out my D. We kind of do these in a weird order. Because my D tells me kind of how much up this midline needs to go, right? Normally my sine and cosine have this midline at 0, but I need to move it all the way up. So how far up do I need to move that? Let's see. Well, first off, what is this value? If my high, this is my high happens up here at 83, and my low happens down here at 40, then this midline is going to be like 40 plus 21.5, right? This is like my 21.5 distance. So it's going to be 61.5. I'm taking my low and then I'm adding my amplitude. Or I could take my high and subtract my amplitude and get there too. But that tells me actually my midline is how much vertical shift that we're doing. So that tells me that my D is, let's just write how we got that. It was 83 minus 21.5, or also we could do 40 plus 21.5. And either way, we get that D is 61.5. Cool. Then we need to do our shift. And I guess before that, we need to decide if we want to model this with a sine or a cosine. If we modeled this with a sine, then we needed to have shifted a point that was right here all the way to here. And if we model it with a cosine, we need to get a point that was here all the way to here. I feel like that one might be easier to do if I first reflect it and then just shift it over a little bit. So let's think about that. So if we do this with the cosine, let's kind of fill in the pieces that we know. I know I'm going to look at the cosine of, let's see, I said that my b would be pi over 6, and then x minus, I haven't figured out that number yet. I said that my vertical shift was going to be 61.5. And I said that my amplitude, or at least the absolute value, would be 21.5. And if I model this with a cosine, remember cosine normally starts up like this, and I have something that's a little bit more like this. And so I need to think about reflecting this over the x-axis. Okay. The last thing I need to figure out is my usual cosine would have been more like this, right? It has its low point on my y-axis, and I need my low point shifted to the right a little bit. And how much is it shifted to the right? Well, January is 1 in this, so it's shifted over 1. You know, I don't have my low at 0, I have my low at 1. So I would need to shift this to the right 1, which would mean I'd have a -1. So this is what is telling me we're going to shift right 1. So C is 1. And so what you might do actually is put this on Desmos and see how we did. So let's go ahead and do that real quick. Let me pause to get this ready. All right, let's take a look at this graph together. So first, let me tell you a little bit how I put this in Desmos. You can always click plus and then table, and that's kind of a quick way to put in a lot of points. So I put in all my x's and my y's here, and so that's what we're seeing here. I did also change my window to be a nice view for that. And then I went ahead and typed in this formula that we have here. And if I show that there, now I can see that this is a pretty good model for this. It's not perfect, but it's a pretty good model. This one is pretty exact. This one is pretty exact. We get a little bit off here and a little bit off here. So maybe there's some really slight changes that we could do to make this way perfect. But this is a pretty good model. And especially this is nice because now, even though I just use 1 year's worth of data, I can now project into the future and say, what about in future months? What do I expect the temperature to be? And we can continue this forward. Now, it's not always the same, right? Maybe year to year, there's different highs or different lows. It's not perfect, but it's a pretty good estimate of what to expect.